Hey everyone, welcome back and let's write some more neat code today. So today let's solve the problem, time needed to buy tickets. So the premise of this problem is similar to the last one. We still have kind of a queue of people. In this case though, we're given two inputs. We're given an array called tickets. Now this actually represents the number of tickets each person wants. So the first person in the queue wants to buy 2 tickets. The second person in the queue wants to buy 3, and then the last one wants to buy 2. And so the queue is ordered in this way. The problem is that a person can't buy 2 tickets. They can only buy 1 ticket at a time. So this person buys a ticket. Now they only want 1 ticket. Okay, now this is the beginning of the queue. So in a sense, this person goes to the end of the queue, and we could model it that way if we wanted to. We could use a built-in queue data structure. That's perfectly valid, but the problem is easier than that if you can recognize a couple things. And I'll try to explain the intuition of how we can make those observations that will make us be able to solve this problem more easily. So for now, let's just say, okay, this person bought 1 ticket, now they only want 1. We can, instead of manipulating this like a queue, we can just have a pointer, right? So this pointer will now be over here. Next person wants 3 tickets, but they can only buy a single one, so they buy 2. Now, we're over here. This person wants to buy a ticket. They can only buy 1. So now this is what our queue looks like. Everybody still needs to buy at least 1 more ticket. Now next, this person could buy their last ticket. Now they only want 0 tickets. Now we're here. This person buys a ticket, only 1 ticket. This person buys 1, 0 tickets left. So now it kind of becomes useless to have a pointer because not every pointer is going to be at a valid value. This person wants 0 tickets. We can skip them now. We can automatically go over here. This person wants to buy a ticket, so they buy it, and now we're left with all zeros. Nobody needs any more tickets. So that's how we could run the simulation if we wanted to with an array. And again, you could also more appropriately run the simulation if you are using a built-in queue data structure, because you could pop from here and then push here, pop here, push here, etc., etc. If we ever got to a 0, then we pop it, and then we have no need to push it to the end of the queue. The person doesn't need any more tickets. So that's why it's kind of a queue problem. But this is the observation that we can make that will make the problem pretty trivial. First, I guess we should start with what exactly are we trying to figure out? Like, we're not trying to run the simulation. We're trying to actually answer a specific question. And that question comes from the second input parameter. So that parameter in this case is k equals 2. What that means is the person at index 2, which is this, because we're 0 indexed. This is 0, this is 1, this is index 2. We want to know how many turns does this person have to wait to buy their tickets. Now, that's not how they really phrase it. They say 1 second, so I guess I'll stick with that. So every time we want to buy a ticket, it takes 1 second. So this person to buy a ticket, now they only want 1 ticket, that took a second. Now this person wants 2 tickets left, now 2 seconds have passed. This person wants to buy a ticket, now they only want to buy 1 ticket. So doing those 3 turns, those 3 steps took 3 seconds. And if we continue again, this person buys a ticket, 0, this person buys 1, 1, this person buys a ticket, now 0. So in total, it took 6 seconds before the person at index 2 bought all the tickets that they wanted. That's the question we're trying to answer. How many seconds does it take before this person buys all the tickets that they want? And if our parameter k was equal to index 1, then we'd be asking how many seconds before this person buys all the tickets that they want. It would take 1 additional second, because now they get to buy a ticket, so then it would take 7 seconds. So at first, it seems like you have to run the simulation to answer the question, right? But there's a pattern here. Let me kind of explain it to you. It took 6 seconds for this person to buy both their tickets. Why is that? Let's dissect it. First of all, for this person to buy their tickets, the people ahead of them have to make a move. So this person wants 2 tickets. Therefore, everybody before them has to go twice, like through that line of buying tickets. This person would have to go twice, this person would have to go twice, and then this person would have to buy both of their tickets. After these people have gone twice, it would take 6 seconds. But is that always going to be the case? Consider this. What if the value here was actually a 1? This person only needs to go and buy a single ticket. Well, they're going to buy that ticket in 1 second, and then they're never going to buy another ticket. So then they wouldn't need any more tickets. This person, though, would still have to go ahead of this person twice. So it would take 1 second for this person, it would take 2 seconds for this person to go twice, and then this person would buy both of the tickets that they want. That takes 5 seconds. What's the pattern? What's the difference between this new example I showed you and the previous example we were looking at? Pretty much this. We go to index K, this is the person we care about, then we go through every person before this person, and we add to our total, which I'm going to call the result. So this is the number of seconds we're trying to total up, and we're going to go through every value, and we're going to ask a simple question. Is this value less than the value at index K? If it's less than the value at index K, we take this value itself and add it to the result. It's just 1. We go to the next value. Is this value less than the value over here? It's not. So what do? It's 3. But does this person really have to buy 3 tickets before this person can buy 2 tickets? Nope, they definitely don't. What we're recognizing here is that the person at index K is the bottleneck. So either we will take a value here, which is smaller than 2, and add that to the result, or this value is greater than 2, in which case we're just going to still add 2, because we only need this person to go twice before this person can buy a ticket. And to finish the example, we get to the person at K and add their value, which is 2. So in this case, it would take 5 total seconds. Now let's quickly go back to the previous example where this was a 2, just to spot the edge case, where this value is equal to the value at index K. In that case, we also would add that value. So basically, if this is less than or equal to the value at K, we add that to the result. And if it's greater, we will just add the value at index K to the result. And for this value itself, we'll add that as well. So in this case, we would get 6. There's one last thing that this first example doesn't actually illustrate for us, because it's a special case where the index that we're considering only has people in front of them. What about if there were people behind this person? That matters as well. So let's change this example to K equals 1. Now we want to know how many seconds does this person have to wait before they get to buy all 3 tickets. So let's follow what we had before to our result. We're going to go through every value. We're going to see this one, it's less than or equal to this. So we're just going to go ahead and add 2. This person definitely needs to buy 2 tickets before this person can buy 3 tickets. Okay, now we get here. This value is 3. It's less than or equal to 3 technically. So it does follow our rule. So 3 is going to be added. That makes sense because this person, of course, needs to go 3 times before they can buy all 3 tickets. Now, though, when we get behind, in this case, it is true that this person needs to buy 2 tickets before this person can then buy their 3rd ticket. So technically, we do add this value to the result. But is that always going to be the case? Let's change the example for a second. What if this was a 3? Does this person need to buy 3 tickets before this person can buy their 3rd ticket? I mean, this person is ahead of this person. So really what's true is this person only needs to buy 3 minus 1 tickets before this person gets the 3rd turn. So for any value that's going to come after index K, if that value is less than the value at index K, which it was previously when this was a 2, we will go ahead and take that value and add it. But if that value is greater than or equal to this value, then we can ignore that value and just replace it with this value minus 1. So 3 minus 1, which is a 2. So in that case, we would add 2 here, and it would only take 7 seconds for this person to buy all the tickets that they want. Just to make this even more crystal clear, let's replace this value with a 10. This person wants to buy 10 tickets. So are we going to add 10 to this? No, of course not. We don't need this person to wait 10 seconds before they buy their 3rd ticket. We only need this person to buy 2 tickets before this person can buy their 3rd. So again, we would replace this value with the value that goes here, minus 1. So we'd put a 2 over here. So it's all about how we add values that come before index K and add values that come after index K. So knowing that, I'm going to go ahead and code it up. This is a linear time algorithm, by the way, because we're just iterating once. We're not doing like the entire simulation, and it's constant space because we don't really have any data structures. We're just keeping track of what the result is. Okay, so I'm gonna initialize the result to 0. This is like the number of seconds that it's going to take for the person at this index to buy all the tickets that they want. And this is what we're going to end up returning. So now I'm going to iterate over every position in the input length of tickets. And I am keeping track of this index because we know it kind of does matter, because we know there's two cases. Either I is greater than or equal to index k. And the reason I'm saying equal is because the value at index k matters as well, or it's not. And the else case is that the index I, well, I guess actually this should be the opposite. We want this to represent where the index has not passed k, and this is going to represent when the index has passed k. So what we learned is everybody before and equal to k has to buy tickets before this person. And either the value, so let's say nums of I, is either equal to k or it is less than k. So basically what we're saying is we want to take the minimum of these two values. We could write an if statement if we wanted to, but the easier way to code this up is to take the minimum. So either this value is less than this value, or this value is greater, in which case we want to replace it with this value. So what we're saying is we want the minimum of these two. That can be taken pretty easily. This is basically the number of times that this person would have to buy a ticket before this person can buy all the tickets that they want to. So this is what we add to the result. And I realize I'm using nums here when we should be using tickets. Sorry about that. Now, the else case is going to be pretty similar. The only thing was that the person at index I does not need to buy this many tickets, doesn't need to buy the same number of tickets as the person at index k. So they only need to buy at most this many minus 1 tickets. So either this value is less than this value, which is fine, or it's equal to this value or greater than this value, in which case we want to replace this one with this minus 1, just like we kind of did in the drawing explanation. I know this is a little bit different than how we kind of talked about it in the drawing explanation, but the core principle is kind of the same. The only difference is I'm using the min function here when we could just be using an if statement. Like we could have been checking, is this less than or equal to this, and could have done the same thing like up above, but to be more concise, leaving it like this. So this is the entire code. Let's go ahead and run it to make sure that it works. And as you can see on the left, yes, it does. If you're preparing for coding interviews, check out leetcode.io. Thanks for watching, and I'll see you soon.